welcome to lecture 23 of Fox. And as you can see, Orange Malik is here because today we're going to be discussing what is computing. So you're walking down the street and someone asks you, what is computing? And in your mind you have this vague idea. There's an input and you feed it into a computer and maybe it changes it or produces an output, And as computer scientists, we need to have a firm idea. We need to pin down exactly what is computing. And that's what we're going to do in this lecture. And it involves this notion of languages. So, but before we pin down what exactly is computing, what exactly is a computing problem, let's review what we were talking about last time. We were talking about, infinity, which is this very abstract beast. It looks like, what does it have to do with computing? Well, it turns out that an algorithm is in some sense a finite answer to infinitely many questions. Okay? And so infinity plays a role in computing. And in fact, last time we saw that there are two fundamental sets in computer science, the finite binary strings. Those are programs. Okay? Any program is a finite binary string. And we showed that finite binary strings are countable. So that's one level of infinity. And then there are the infinite binary strings. Okay, what are infinite binary strings? For example, what does an algorithm do? It produces an answer to infinitely many questions. And you can list all of those answers in an infinite binary string. Something like a function on n, a binary function on n. An answer to infinitely many questions. What is f of 1? What is f of 2? What is f of 3? And so on. What is f of 752? Okay. Now, if we were to implement f in a computer, we have to implement it as a finite binary string, as a program. And it has to be able to provide the answer to infinitely many questions. But we saw that the infinite binary strings are uncountable. So the number of functions on n, for example, the number of binary functions on the natural numbers is uncountable. And so the conclusion is quite stunning, but yet we arrive at it in this very simple way by analyzing this abstract beast called infinity. The conclusion is that there must be some, in fact many, uncountably many functions that we cannot compute with programs. Okay. Many things we cannot compute. Okay. So, in order to sort of flesh out that discussion, we need to have a firm idea. We need to pin down exactly what is computing. What is a computing problem? Okay. And in doing so, we're going to be led to this simplification of a computing problem, which happens to be general enough to sort of encompass everything that we would like to compute. These are called decision problems. They can be encoded in what are called languages. And then we have this nice way of describing the complexity of a computing problem by describing the complexity of the language. And it turns out a language is just a set. So if we know how to manipulate sets and we can understand the complexity of sets, then we can understand the complexity of computing problems. Okay, so let's go to the board. Let's talk about a simple computing problem. So I give you a number n, and I ask you, is it prime? Okay. So, and your goal is to answer yes or no. So decide yes or no is, some natural number prime. Okay. And, let me underline the word decide, because that's related to the yes or no. You're to decide between two options. Okay, now let me show you a simple way in which we can approach this problem and try to solve it. Okay, and what I'm going to do is I'm going to list the primes in increasing order. So let me call this list, this set L prime. Okay, is the set of primes in increasing order: 2, 3, 5, 7, 11, 13, 17, 19, and so on. Okay, and given this list in increasing order, okay, and by the way, the fact that I'm using numbers is not necessary. I could use binary strings, so the binary representations of numbers, and we will soon go into binary because that's what computers are all about. Okay, but given this list, you could say, okay, how does that list solve the problem? So I'm supposed to decide yes or no, is the number n prime? Okay, so let's see how it would work. So let's try 11. Okay, so input n equals 11. And here's my strategy. I'm going to start at the beginning of the list. Okay, and go one by one. And if I find 11, I say, yep, I found 11 in the list of primes. So therefore, 11 is prime. So here I go 2, 3, 4, 5, 7, 11, each time checking. Okay, and in this case, I found the match. And so I output yes. And it's correct. Okay, let's take another example. 12. Okay, so I start at the beginning of the list. I see 12, not 12, not 12, not 12, not 12, not 12. But when I get to 13, not 12, but also I can at the same time check whether the number I'm at is greater than equal to n. And in this case, 13 is greater than equal to n. So immediately I'm going to output no. Now, why is that? Okay, so you might stop for a couple of seconds and think, why is that? And it has to do with the fact that, I listed my primes in increasing order. So this algorithm works. Okay. Now, you might say, well, this is not a very smart way to solve this problem. Okay, yes, I agree. There may be other smarter ways to solve the problem, but this is certainly one approach, and it gets at sort of what is the notion of computing, what is at the heart of this question, what is a computing problem? Okay, and that's, we're ultimately going to build our way towards this concept of what's called a language. Okay, but we're not there yet. And that's why I chose to solve this problem in this way, because it illustrates that concept. Okay, for a simple problem that we're familiar with. Let's take another problem. Okay, so I'm going to draw here a push light. So what do I mean by a push light? It's one of these lights that, starts in the off position and has a switch, and every time you push the switch, it toggles between on and off. So it's off. If I push, it's on. If I push again, it's off. If I push again, it's on, and so on and so forth. Okay, so we can imagine, a computing problem, a very simple computing problem. I'm going to tell you n, the number of pushes, and you're supposed to tell me, is the light on or off? So decide. Yes or no. Is the light on for n, which is a natural number, pushes? Okay, and you might say, okay, that seems like a reasonably simple problem. Let's try to solve it in this exactly the same way. Okay, so so what is n? So n can either equal 1, 2, 3, 4, and so on. And then this time I'm going to explicitly represent n in binary. Okay, and what I'm going to do, just like here, I listed the numbers which are prime. Let me list the numbers in binary for which the light is on. So let me call that L push because I need a name. So L push is, so if you push once, it's on. If you push twice off, 3 times, it's on. If you push 4 off, 5 times, it's on. 1, 1, 1, sorry. 6 off, 7 times, it's on. So 1, 0, 0, 1. Okay, and 8 off, 9 times on. 1, 1, 0, 1. And so on. Okay. We can also add in here, technically speaking, if I'm thinking of these as binary strings, I can prepend any number of zeros and it doesn't change the number. So this set would also contain 0, 1, and it could contain 0, 1, 0, 1, and it can contain 0, 0, 1. So I can prepend any number of zeros and it's still the same number. Okay. Now, can I solve the problem in the same way? Well, basically, yes. So, these are increasing. So let's assume that we have ordered the strings in some kind of increasing lexicographic order. And so, if my input n is equal to 1, 0, 0, 1, so I go, no, it doesn't match, no match, no match, match. So the output here is yes. Okay. And if I go with n equals, let's say, 1, 0, 0, 0. So I go no match, no match, no match, no match, but this is a larger number. Okay, and so I say no. Okay, interesting. Okay, so, here's an example of a computing problem. Make a decision, yes or no. Here's an example of a computing problem. Make a decision, yes or no. Okay, and these kinds of computing problems where, the decision that I'm asking you to make is yes or no, we call those kinds of decision problems, we call those kinds of computing problems decision problems. So these are decision problems. Okay, no surprise. But what I want to point out is something very interesting about decision problems, which is that since the answer is yes or no, okay, I can collect into a set all the inputs for which the answer is yes. I can collect into a set all the inputs for which the answer is yes. And let me just call that the yes set. And this is the yes set. Okay? And why is there a yes set? It's because we're talking about, in this context, in these two problems, we're talking about decision problems. Now, so we may wonder, okay, decide yes or no is n prime. And let's think a little bit about that sentence. Okay, we sort of took it for granted that we understand this as a computing problem, but then someone who is not as knowledgeable as you might come and say, what does it mean? Prime. Decide yes or no is n prime. And oh, well, prime, well, that means its factors are only one or itself. Oh, what are factors? Oh, a factor is something where if you multiply that number by an integer, you recover the original number. Multiply? What does multiply mean? Okay. And so what you realize is that in this definition of a problem, there's embedded a whole lot of mathematical machinery, heavy math, multiplication, division, prime, and so on and so forth, that we're assuming of the reader. Okay. Let me give you an alternative way of specifying this problem. Okay. Don't tell me anything about primes and this and that and, natural numbers. I might ask, what's a natural number? Okay. I might be completely knowledgeless. Okay. Can I specify this computing problem to someone who is more or less completely knowledgeless? And I say the answer is yes, I can. How? I just tell you the yes set. I describe for you the yes set. So if I just gave you this yes set and said, there's your problem. You say, well, what's the problem? Well, I gave you a set of inputs, and later on, maybe at 4 p.m., I'm going to give you an input, and you need to return the answer yes if the input I give you is in the set, or no otherwise. Very simple. I don't need any mathematical baggage. No knowledge of what is prime, no knowledge of what are push lights. In other words, what I'm trying to convince you is that another way of specifying that problem, because it's a decision problem, is by just telling me the yes set. And you're done. Okay? You've told me the problem. You've told me the inputs for which the answer is yes. That's equivalent to telling me the problem. Okay? And so that's one thing very nice about decision problems. They can be effectively characterized by just specifying the yes set. Okay, so now let's look at some other slightly more complex problems to see if something similar is going on there. Okay, so I'm going to draw a graph. Okay, so here's a graph, 1, 2, very simple graph, 3, 4. Okay. And let me ask a yes/no question. So decide yes or no is, now technically I would say, is there a path from 1 to 3 of length less than or equal to 3? But that's equivalent to saying, is the distance from 1 to 3 less equal to 3? So is the distance from 1 to 3 less equal to 3? Okay, and the answer is clearly yes, because the distance from 1 to 3 is 2. So the answer here is yes. Okay. So the answer here is yes. Put it in red. Yes. Okay. Now, this is an example, just like this and just like this, of what I call decision problem. So let me, label this as a decision problem. Okay. What other kinds of questions might we like to ask on this graph? Okay. Well, we might say, well, I don't want to know if the distance is less than or equal to 3, or I might have asked the question with, is the distance less than or equal to 19? Okay. What I would like to know is, what is the distance? Okay. So, what is the distance from 1 to 3? Now, it should be clear to you that if I told you the distance from 1 to 3 is at most 3, you don't know much about the distance. You just know that it's at most 3. It doesn't tell you what is the distance. Okay. So, I'm going to label this kind of question, what is the distance? I'm going to label it optimization. Sometimes you might see it referred to as sort of search. Okay, and typically when we're searching for something with some property, some sort of optimality property. Okay, so in this case we're searching for the path. Okay, that's what tells us the distance. We're searching for the path with the minimum number of hops from 1 to 3. Minimum number of hops is what makes it optimization. We're trying to optimize. We're trying to minimize the number of hops. Okay? So this is called an optimization problem. Okay? And if you think about it, many, if not almost all the problems, all the questions that we would like to have answered by computers in the real world involve some form of optimization. For example, what's the distance from Albany to New York City? Okay, that's optimization. Okay, what's the maximum number of packets that I can send in the ISP router network from Albany to Washington, D.C.? Optimization, maximum number of packets. Okay, Google search. Okay, so what is the web page that most matches my search query. Most matches my search query. Optimization. Okay? So pretty much almost anything we like to solve in the real world is optimization. So let's agree, or at least, concede that, if we could solve all kinds of optimization problems, then we are basically able to do computing. That's what essentially computing is sort of capturing in the real world. Okay? But you will observe that optimization is very different from decision. Okay? So what is the distance from 1 to 3? The distance from 1 to 3 is 2. So the answer to this question is 2. Whereas the answer to this question, the decision question, is just a simple yes or no. And in principle, there could be many possible answers to the optimization question, but for the decision question, just one of two answers, yes or no. Okay. Now, observation. Observe. Okay. If I tell you the answer to the optimization problem, the distance is 2. Do we know the answer to the decision problem? Is yes or no, is the distance from 1 to 3 less than or equal to 3? And the answer is, we can trivially conclude that the answer is less than or equal to 3 because 2, which is the distance, is less than or equal to 3. So the optimization problem implies the decision problem. So what am I saying here? Why this implied? What I'm saying is that if you could solve the optimization problem, you immediately get the answer to the decision problem. So in some sense, the optimization problem is stronger, harder, more general than the decision problem. I.e., if I knew how to solve the optimization problem, you've pretty much solved all my needs. I can answer the decision problem at will, because I know the answer to the optimization problem. I could answer the decision problem. Okay? So it looks like optimization problems are very different from decision problems, at least in terms of, being able to solve them. Looks like decision problems are much easier than optimization problems in terms of being able to solve them. Okay? Now what I want to show you is the sort of stunning conclusion that no. Okay? If I can solve the decision problem, I can solve the optimization problem. And here's the simple idea. So decision problem. Decide is yes or no. Okay, so let's put the yes or no. Is the distance from 1 to 3 less equal to 0? Less equal to 0, that takes into account the possibility that when I ask you this question for the decision problem, I might have put in the same nodes. I might have put in 1 and 1. Well, we don't know, right? Maybe 3 is just another label for 1. Okay, so is the distance less equal to 0? Well, in this example, clearly no. Okay, no. Okay. Decide, yes or no. Decide, yes or no. Is the distance from 1 to 3 less equal to 1? Well, clearly no. Okay. Decide, yes or no. Is the distance from 1 to 3 less equal to 2? Yes. Yes. Notice that the first time the yes occurs, I can now answer the optimization problem. So the optimization problem is answered by 2. Okay. So what have I done here? What I've done here, let me remind you exactly what's going on. I'm pretending, okay, now in this example, it's clear how to solve the problem, but I'm pretending I have a solution to the decision problem. I'm just pretending. Okay. So forget about the fact that I can look at the graph and say yes or no. Just imagine I have a way to solve the decision problem that always gives me the correct answer. That's what it means in some sense to solve the decision problem, right? So decide yes or no. So it said no, then it said yes, and then I can, at the end of this box, okay, I can now answer the optimization problem. Okay. So what does this mean? This means that by repeatedly using, a computing solution to the decision problem, I can at the end of the day answer the optimization question. What that means is that if I have this ability to solve the decision problem, I do indeed have the ability to solve the optimization problem. Isn't that interesting? So, from the perspective of what we can solve and what we cannot solve, okay, if we can solve the decision problem, we can solve the optimization problem. So, it's a very surprising conclusion that the decision problem actually implies the optimization problem. Okay? So it's no
harder or no easier than the optimization problem. Optimization and decision, at least in this context, are basically the same. Okay, and that leads us to the definition of a computing problem. A computing problem is a decision problem. Okay. And sort of this discussion is to convince you that, we haven't lost any generality with respect to the kinds of problems that we can solve in the real world. So in the real world, maybe we prefer to solve optimization problems. No big deal. For any optimization problem, there's sort of a corresponding decision problem. And if you can solve that decision problem, you can solve the optimization problem. Okay. And so, we can focus our study of what is a computing problem to just decision problems, and what is computable to just what decision problems are computable, whatever that means. Okay. And this is a definition of what a computing problem is that's very precise. It's a decision problem, and we're going to make it even more precise. It's a decision problem, and this is a definition that has withstood the test of time. Okay. So, it's not just me making it up. This has withstood the test of time. It applies to computing in the real world and solving real problems, for many, many, many decades. Okay, now, we get back to this, decision problem and this notion of the yes set, okay, and we see that an equivalent way to define a decision problem is to just tell me what is the decision problem's yes set. Okay? So an equivalent way to define a decision problem is tell me / describe the problem's yes set. Okay, now we'll focus mostly on describing the input using binary strings. So tell me which binary strings are in the yes set. And this is a way of defining the problem which doesn't need any vocabulary. I don't need to tell you what's prime. I don't need to tell you what a push switch is. I just tell you, here's the yes set. Boom, I've defined the decision problem. Here's the yes set. Boom, I've defined the decision problem. Okay, can we do that for our graph decision problem? Because that looks much more complicated. Actually, it's not. Okay, because, although I sort of describe this problem, this decision problem, by drawing a picture, anything we want to submit as input to a computer, even a picture like this, has to be submitted as a binary string. Or, and the way we typically, formulate it as a binary string is to first formulate it in some more sort of, familiar string, as in some more familiar language as a string, and then convert it to binary, for example, using the ASCII code. So let me show you how this decision problem can be formulated as a string. Okay, so formulating the graph problem as a string. Okay. So, the first thing I have to tell you is, what is the graph? I have to represent the graph as a string. So one way I can represent the graph is to first list, so I'm going to put quotes, but typically we don't put the quotes. I'm going to put quotes just to indicate that it's a string. So let me first tell you what are the edges. What are the vertices? So the vertices are 1, I'll comma separate them, 2, 3, 4. Okay. Then I'll put some kind of a divider. Okay, now all of these things will ultimately have to be converted to binary, but we know how to do that, because I'll put a divider. Now I'll tell you the edges. So the edges are, so this is telling you the nodes. Now the vertices, now I'll tell you the edges. 1, 2, semicolon, 2, 3, semicolon, 3, 4, semicolon, 4, 1. Okay? So there, I've specified the graph for you by telling you what are the vertices and telling you what are the edges. Okay. If I wanted to, I could make the formatting much more pleasant by putting, parentheses to indicate the edges. Let me just do that just so that there's no confusion. So here are the edges. Okay. But ultimately, all this can be converted to a string, a binary string. Okay, now, now I've told you what the graph is. Now let me tell you what my question is. Well, I have two vertices, 1 and 3. So the vertices of interest are 1 and 3. Okay. And the distance I'm interested in is 3. Okay. So, if I were to show you this string, okay, it can be translated as, in this graph, with these vertices and these edges, so here we have vertices, here we have the edges, here we have the vertices of interest, the vertices of interest, and here we have the distance of interest. Okay, so we have the vertices, the edges, the vertices of interest, the distance of interest. So in this graph, so this string represents the question. Okay, this string in this graph with these edges, okay, between these two vertices is the distance at most 3, and the answer is yes. Okay. So pop quiz. So let me give you a pop quiz. Quiz. Just to show you that that entire question can be embedded as a string. Yes or no? Okay, so yes or no? Or no? Okay, answer yes or no, and here is the question. 1, 2, 3, 4, 5. Separate. Okay, 1, 2, 2, 3, 3, 5, 3, 4. 1, 2, 2, 3, 3, 5, 3, 4. Separate. Okay. So yes or no? 1, 5. 1, 5. Separate. 2. Yes or no? Pause the video for a few seconds. Okay. And try to solve this question. And answer yes or no. Okay. So 1, 2, 3, 4, 5. So now if you're coming back, what are we asking? We're asking yes or no. In this graph with these vertices and these edges, okay, between the two special vertices, 1 and 5 is the distance at most 2. Yes or no? So we're asking yes. Did you say yes or did you say no? The point is that the question we're asking can be formulated entirely as just a string. No need of pictures, no need of anything. Okay. Here, the question we're asking is embedded in just the input string n. Okay, the input is n. Here, again, the input is n. Here, the input to the person or the computer or whatever it is that's deciding is this complicated string. Okay. So now let me define the yes set for that problem. Okay. So let's define the yes set. The yes set. Okay. Is for the graph problem. For the graph problem. It's the set of all strings of this form. All strings of the form. Okay, vertices, edges, okay, V1, V2, 2 vertices, and distance. So all strings of that form for which the answer is yes. For which the answer is yes. Okay. So now you want to have your question asked. You want to ask your question and have it answered. So decide. So you have a graph, your favorite graph, and you want to know if the distance between you and, let's say, Joe Biden is at most 19. Okay. So you have to formulate your graph as a string and then send it into this, whatever it is that can solve the problem, and ask, here's my input string. Tell me whether or not it's in your set of strings for which the answer would be yes. Okay, that would be an extremely inefficient way to solve this problem, but it is a way to solve this problem. Okay, so I want to emphasize that we discussed the fact that the decision problem can be used to solve the optimization problem, that the optimization problem that can be used to solve the decision problem. I'm showing you ways to solve the graph distance decision problem, ways to solve the primality problem, ways to solve the push problem, and you might look at them and say, those ways of solving the problems are not very efficient, they're not very smart. Very good. Okay, good observation. So we are not talking about efficiency. So indeed, when I showed you how to solve the optimization problem using the decision problem, we called the decision problem multiple times. In that example, it was 3 times. Okay. So it took us longer to solve the optimization problem by invoking the decision problem than just solving the decision problem. That's perfectly fine. Okay, so yes, it may be costlier, it may be computationally less efficient to solve the optimization problem versus the decision problem. And in that respect, maybe the two problems might differ. Okay? But for the moment, we are not talking about efficiency. We are talking about what is solvable. Okay? And so this approach to solving the graph distance problem is a perfectly valid approach. You formulate your string, and I'm going to search this set. Okay? And if I find it, then I answer yes. If I can show that it's not in this set, then I answer no. And my approach may not be efficient, but it's a valid approach. Okay. So let's conclude. So, conclusion. And summary. So, summary. What's a computing problem? What is a computing problem? Okay, and this has stood the test of time. It's a decision problem. A decision problem. What's the input for a computing problem? What's the input? It's a string that represents the question you're asking. A string that represents the question. Okay, so in the case of the graph distance problem, the string represents both the graph, the vertices, string, okay, represents the graph, G, the vertices of interest, sorry, the graph G, the vertices of interest, and the distance. So everything that pertains to the problem and is required in order to answer yes or no is embedded in the string. So that's the input. Okay. The output, because it's a decision problem, is yes or no. Now, in English or in mathematics, we like to represent the decision problem in English language, like, determine if n is prime, but that's a very sophisticated concept. Is n prime? Okay. And so the simplest way to represent a decision problem, okay, so how to represent a decision problem? Represent decision problem. The simplest way to represent a decision problem is with its yes set. Okay, which is the set. So the inputs are strings, so the set of inputs, i.e. strings, for which the answer is yes. Okay. A very simple way to represent any decision problem, which is our definition of a computing problem. And now I want to sort of pause and emphasize that this is a very well-defined way of defining any computing problem. I don't need to understand language. I don't need to understand anything. Okay? Just tell me what is your yes set. That defines the problem in its entirety. Okay? Your yes set is, okay, your yes set is, my yes set is, so yes set, yes set is equal to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. Okay? Strings of ones, perfectly valid computing problem. What does that correspond to in the real world? Well, it may correspond to a problem in the real world or not that we are not familiar with. For example, if we are not familiar with what is a prime, but once you tell it to me in the form of a yes set, you've specified the problem. It's a very well-defined problem. We've pinpointed, we've precisely defined what is a computing problem. A computing problem is a decision problem, i.e. a yes set. So let's restate that. A computing problem is a yes set. And that's a very abstract, very precise definition of what a computing problem is. And what's the task? The computing task given an input string, and we'll focus on binary strings, just like here, strings of ones, because any, yes set which is composed of complex strings, you can convert to binary. So given an input binary string, determine, if, so let's call the input binary string, let's call this W. Determine if W is in your yes set. Okay. And that's it. Very precise definition of a computing problem. Okay. And, we have notation for this. So it's all nice and intuitive to call it a yes set. Okay. But we typically, so definition. So we have a notation, a formal notation for what, we've been calling a yes set. So definition. A yes set, a language. A language L is just a collection of finite binary strings. Is a collection of finite binary strings. Okay. And a yes set is also a collection of finite binary strings, the inputs that correspond to yes for any specific problem. So what that means is that any language could be a yes set. Okay? So a language L could be a yes set. Any language L could be a yes set. Okay? And we just might not know what problem it corresponds to, but the problem it corresponds to is the yes set. So that now becomes the definition of the problem. Okay? So any language could be a yes set. And so now we can reformulate the definition of a computing problem. A computing problem is a decision problem. A computing problem is a decision problem. Okay? Or a computing problem is a language. Why? Because a decision problem can be represented by a yes set, but that's just a language. And any language could equally well function as a computing problem. So it's an abstract definition of computing problem. So a computing problem is a language. L. A very abstract definition of a computing problem. We have this concrete, very precise definition of a computing problem now, which is just a set of binary strings, a language. Okay, and so to specify a computing problem, you have to specify that, set of strings, and now we're going to do some examples of that. And then what does it mean to solve the computing problem? So to solve the computing problem means you have to give a procedure for determining if the input, so I give you an input string now, W, so you have to give a procedure for determining if an input string is in the set. So you need a procedure to determine if input W is in your language, your set of strings that defines the problem. Okay? This is the language now. Okay, so let's look at, now we can just specify problems without talking about primes or graphs or anything. We can just specify problems by specifying the set. So let's look at some example languages. Okay, so example languages. Okay, and let's start simple. Okay, so, here's a language. Epsilon 1, 1, 0, 0, 1. Okay, so this is just a finite language. So it's a finite computing problem. So finite language. Okay, let me show you, the set of finite binary strings sigma star. Now we called this B before. Okay, so all finite binary strings. It's a perfectly valid set of finite binary strings. It happens to be infinite, but it's a language. Okay, so this has the empty string 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, and so on. Okay, so this is all binary strings. Okay, and if I wanted to be precise, finite. Okay, so any computing problem contains only finite binary strings. So a language is finite binary strings. There's, an input to a computing program, an input to a procedure can never be an infinite binary string. So the yes set of any, problem is always finite binary strings. Okay, so let's continue. The prime, okay, is equal to, 2, 3, 5, 2, 3, 5, 7, 11, and so on. Okay, so now I've represented the primes as, finite binary strings. So these are the primes. Okay, so primes as binary strings. Okay, the push light. Okay, so L push. Now, if I wanted to, I could also include the leading zeros, and that would be a different computing problem where I would also allow 0, 1, 0 to be a prime because that evaluates to a number. So, and that's what we will do with the push strings. So L push. Okay, so this is the push light problem. Okay, so basically. The push light problem 1, so all valid strings of length 2 are 0, 1, and 1, 1. All valid strings of length 3 are 0, 0, 1, 0, 1, 1, 1, 0, 1, okay, and 1, 1, 1, and so on. So now this is the number 1 push. This is also the number 1 push. This is the number 3 pushes, and so on. Okay. But I'm allowing trailing zeros in this case. Okay, so I can define any problem I want. This is a perfectly well-defined problem. You can see that these strings are easy to sort of identify the pattern. They all end in a 1, and that's what it means for the number to be odd. So an odd number of pushes gets the light on. Okay, strings that end in 1. Okay, and we can continue. Let me give you a few more examples. So L, let's call this unary, is just the set of strings epsilon, empty, so 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. So either the empty string or just ones. So this is, strings of ones. Okay, L, 0, 1 to the n. Okay, so now I'm using this power notation, okay, to say that you can have either epsilon or 0, 1 or 0, 1 squared. So that's 0, 1, 0, 1. Okay, so this is epsilon 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. Okay. Then one last interesting one. Well, I'll give you a couple more. L palindrome is the palindromes. Okay, so strings which are the same forwards and backwards. So we have epsilon 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, and so on. Okay, so palindromes. So these are palindromes. Okay, now I'll give you one more. The repeated strings, L repeated. So, again, this is a string followed by its repetition. So the empty string is a repeated string, 0, 0, 1, 1, 0, 0, 0, 0, so 0, 0 repeated, 0, 1, 0, 1, so 0, 1 repeated, 1, 1, 1, 1, so 1, 1 repeated. And then we can have 1, 0 repeated, 1, 0, 1, 0, and so on. So these are the repeated strings. Okay. So you can see it's getting a little bit tedious to just list languages, by just, listing them and expecting you to see the pattern. But we have ways of describing languages, using variables that we talked about before. So variables. So using, all the techniques that we talked about for describing strings can be used to describe sets of binary strings, i.e. used to describe languages. So using variables to describe languages. Okay, so we could, describe the unary language as the set of strings W, where W is equal to 1 concatenated with itself n times, where n is greater or equal to 0. So we use this, dot n to mean concatenate. So concatenate with me 0 times gives me the empty string. Once gives me the 1. Twice gives me 1, 1. 3 times gives me 1, 1, 1. 4 times gives me 1, 1, 1, 1, and so on. We can describe because we see the pattern. So whenever we see a pattern, we can use a variable to describe the set. So this language of 0, 1, raised to the power n, so repeated, is exactly concatenation. So in a similar vein, we could say this is the set of strings W, where W is equal to 0, 1, concatenated with itself n times, where n is greater or equal to 0. Okay. Let me define a set that looks similar to the palindromes. Okay. So the set L, which is equal to U concatenated with its reversal. Okay, where U is a member of the set of all strings. Okay, so let's think about what this is. So, if epsilon is concatenated with its reversal, you get epsilon. So this is, nothing. Then you could have U being 0. Okay, so then you have U. So that U 0, 0 reversal is just 0, 0. Okay, U is 1, then you have 1, 1 reversal, which is 1, 1. U is 0, 0, so you have 0, 0, 0, 0. U is 0, 1, so you have 0, 1, 1, 0. So U is 0, 1, and then the reversal of U is 1, 0, and so on. So what you will observe is that this, definition using a variable produces palindromes, but they're all the palindromes of even length. So it's not quite the language of palindromes, it's the palindromes of even length. So these are the palindromes of even length. Okay, so there's nothing new here. Okay? The only thing that's new here is just the definition of a language which is a set of finite binary strings, and any language is a computing problem treated as a yes set. Okay, and here I'm just showing you some sets of finite binary strings, and so you can view this as review of the use of variables for defining strings. Okay, now we also have other ways of defining sets of finite binary strings, and that's what we're going to talk about. Okay. In particular, we're going to now talk about the regular expressions. So if you grew up on Unix, okay, or Linux or something like that, you might be familiar with an expression like ls fox star. Okay, so for those of you who didn't grow up with Unix or Linux, let me tell you what this is. This is saying list. Okay, now list all files which start with fox. So files have strings as their names. So the string, which is the name of the file, must start with fox, and then this star is called the wildcard, which is anything. So it describes a set of strings, basically all strings that start with fox. So the wildcard could be nothing, so fox, fox1, fox01, fox A, fox ABC, fox dash dash, fox dot mp3, and so on and so forth. Okay, so this is a very nice compact way of representing all strings that start with fox. Okay. This is an example of what's called a regular expression. So let's erase, come back, and talk about regular expressions. Let me tell you about regular expressions. And I took the liberty to write one here. Let's not focus on that for the moment. At a high level, regular expressions are a very powerful way of describing a language. Now, we saw a very simple example here, ls fox star. That was a fox star is a regular expression, and it defines a set of strings. The set of strings that satisfy fox star, i.e. start with the characters fox. Okay, any fox plus anything, fox followed by anything, satisfies that regular expression. Okay, now, so why are we continuing to describe sets and sets of binary strings and so on and so forth? We already saw sets. We're familiar with sets. Let's move on, you might say. Well, now we've linked, languages, i.e. sets of finite binary strings, to computing problems. And so if we want to be able to specify all kinds of different computing problems, we need ways of describing languages, because a language is a computing problem. To define a computing problem, you just tell me it's language, it's yes set. Okay. And so let's talk about regular expressions. We'll talk about an example, okay, and after we work through this example slowly, you'll have everything you need to know about regular expressions. Okay, so let me read out for you this regular expression. Now let me sort of mention once and then forever we will continue to abuse notation. So this is an abuse of notation. I'm saying that a language is equal to a regular expression. Technically, that's not quite correct, because a language is a set of finite binary strings. It cannot equal a regular expression. This is a description of the language. Nevertheless, we will abuse notation and say this language equals, the set described by this, funny thing on the right. Okay? Now let's walk through this funny thing slowly, and at which point you'll have everything you need. Okay. So we start with a set. This is the set 1, 1, 1. Well, any set of binary strings is a language. Okay, so this is an example of a language. Here's another example of a language, 0, 0, 1. Okay, here's another set. Here's another set. So the building blocks of regular expressions. So the building block. Okay, these are finite languages. Finite languages. Okay, and in our example, we have the finite languages 1, 1, 1. We have 0, 0, 1. Okay, we have 0, 0. That's a set, just one string. And we have 1. Okay, now what we do in a regular expression is combine these finite sets. So the finite sets are the building blocks. We combine these finite sets using set operations. So what are the operations we're familiar with? We're familiar with union, complement, intersection, and complement. Okay, so these are standard set operations. Okay. Now let me just mention, but very quickly, the traditional form in which regular expressions are defined does not include intersection and complement, but you could. We're basically doing the same thing. It's just more convenient to also allow intersection and complement. Okay, but having mentioned that, let's go ahead and use intersection and complement, even though traditionally they don't use intersection and complement. It's a little bit more complicated to implement intersection and complement. That's why. But okay, we'll go ahead and use them. It's easier for us. Okay, and then you combine these finite sets. You can take unions, you can take intersections, you can take complements. So here we see a union. Okay, here we see a complement. Okay. But there are some other interesting things going on here. So there's a concatenation. So we're familiar with concatenating strings. You want to concatenate W1 with W2. W1 and W2 are strings. You just, you write down W1 and followed by W2. Okay. But here, this is a language. Okay. It's a finite language. Okay, and here we're concatenating this finite language with something that looks like a language. So we can take these finite languages and concatenate them. And you might say, what? What does it mean to concatenate a language with another language? Okay, so we have concatenation. And we're going to have to define what that means for languages. We know what it means for strings. Okay. And then there's another funny operator here. So there's complement, good, but there's another funny operator here, star. That's called clean star. And we usually write it by, superscript star. Okay, so that's called clean star. I'll put clean star. Okay, now, you take finite languages, if you combine them with union, okay, if you combine them with intersection, you get back a finite language. But if you take a finite language and take the complement, oh, that's all the binary strings that are not in this language, well, then that gives you an infinite language. Okay. Concatenation of finite languages. Okay, let me tell you what that is. So concatenation. So this is new. Concatenation is new and clean star is new. So concatenation of languages. Okay. And I'll describe it for 2 languages, but we can do it for 3. Okay, let me describe it for 3 languages. So let's say you have, a language L1 concatenated with L2 concatenated with L3. It's very simple. It's a set of strings. It's a collection of strings. Okay, it's a collection of strings W. So it's a language. It returns a language, concatenating 3 languages where, W is the concatenation of 3 strings. W1 concatenated with W2, concatenated with W3, and W and W1 member of language 1, W2 member of language 2, W3 member of language 3. So in words, to get a string in the concatenation of 3 languages, pick any string you want that's in the first language. Anything that's in the second language, anything that's in the third language, concatenate them together, and you've got a string in the concatenation of the languages. Okay, so now let's do some examples of concatenation. So here, so let's do 1, 1, 1. So let's do this language, 1, 1, 1, concatenated with this language, 0, 0, 1. Okay, here's an example. So what do? We can get all strings that are formed by taking a string from here and a string from there and concatenating them. So I can take the 1 and the 0, so I get 1, 0. I can take the 1 and the 0, 1, so I get 1, 0, 1. I can take the 1, 1 and the 0, I get 1, 1, 0. I can take the 1, 1 and the 0, 1, and I get 1, 1, 0, 1. There. That's the concatenation. Okay. So that's concatenation. It's that simple. Okay. But we can also take a concatenation of a language with itself. Okay. So let's look at 0, 1, 0, 0, 1, concatenated with itself. 0, 0, 1. Okay, no problem. You can concatenate any language with another language, and in particular with itself. So this thing is you get 0, 0, you get 0, 0, 1, you get 0, 1, 0, you get 0, 1, 0, 1. Okay, no problem. Now, when you concatenate a language with itself, this is, we say this is the squared concatenation. So we say this is 0, 0, 1, squared. So we do concatenate 2, raised to the concatenated power 2. Okay, so exercise, pop quiz, and I won't even pause the video. Pop quiz, quiz. Okay, what is 0, 0, 1 concatenated cubed? Okay. Now, I will just mention that, now that we're raising to powers, so we have a way to raise a language to a power. It's basically concatenation multiple times. Okay. Language to the third power, concatenate strings in the language 3 times. Okay. We can also raise to the 0th power. This is just by convention. Okay. By convention, to the 0th power, it's just, you concatenate nothing. So this is just the empty string. Okay. That's just convention. Okay. So this is concatenation. Good. Let's talk about the clean star. This is a complicated operation, but it's not that much more complicated than concatenation. So the clean star. Okay, so I'll just tell you what it is with respect to 1. Okay, so this finite language 1. Okay, so 1 clean star. So you see clean star appears in here. Okay, and so so this is basically, you can take any number of strings in this language, concatenate them together, and that's in the clean star, including 0 strings from the language. Okay. So in words, it's the set of strings formed by concatenating any number of strings from 1 star. Any number you want. You concatenate them together, you get a string in 1 clean star. Okay, 1 star. We say 1 star. And in general, you can define this for any language L star. Okay, it's the same definition. You take any number of strings you want from here and concatenate them together. They don't have to be the same string. So you can take 3 different strings from here, concatenate them together, you get something that's in, L star. 5, 10, 15, 20, whatever you want. So, this is, any number of strings, any number of different or the same, any number of strings, not necessarily the same, concatenated together. Okay. And so we write this typically as, we would write this as the union of all possible concatenations, the union of all the sets formed by raising this language to the 0th power, to the 1 power, to the 2, to the 3, to the 4, and so on. So this is the union from I equals 0 to infinity. okay, of L concatenated with itself I times. Okay? So L concatenated with itself I times takes I strings, concatenates them. Okay? But you can take any number of strings you want and concatenate them. So we take the union of all those languages. Okay? So let's see what we get for 1 star. 1 star. Well, you can take 0 strings from the language and concatenate. That gives you epsilon. So that gives you epsilon. Okay? You can take 1 from here and concatenate. That gives you 1. You can take 2. That gives you 1, 1. You can take 3. That gives you 1, 1, 1. And so on. 1, 1, 1, 1. 1, 1, 1, 1, 1. And so on. If we wanted, we could also describe this language 1 star as, W, where W is equal to 1 concatenated with itself to the K times, okay, where K is greater or equal to 0. So that would be using a variable to describe this same language. Okay, 1 star. Okay. So now let's do some examples of clean star that are not as simple as 1 star. So let's do, what else appears? We have 0, 0, 1 star. So let's do, so we have 1 star. 1 star is equal to epsilon 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. Very often, the mistake people make is when they compute the clean star, they forget about the taking of 0 strings from the language. Okay? But you can take 0 strings. So epsilon is always in the star. Okay. Let's do 0, 0, 1 star. So 0, 0, 1. So this is another finite language. So the building blocks of regular expressions are finite languages, and so and then we can do operations on the finite languages, one of which is the clean star, which appears in here. Okay, so let's take the clean star of this. Well, it starts with epsilon. Okay, now you can take 1 string from the language, which is just 1 string. Okay, so we got 0 and 0, 1. Okay, now you can take 2 strings from the language. So you can take the 1 string that we've got and then take these 2 strings and concatenate them with these 2 strings. So we can get 0 concatenated with 0. So we can get 0 concatenated with 0. We can get 0 with 0, 1. We can get 0, 1 with 0. We can get 0, 1 with 0, 1. Okay. And so that's all possible ways of concatenating 2 strings from this language. And then we can concatenate 3 strings from this language. Okay, so let me do that back in black. So we can concatenate 3 strings, which basically says, take these 2 and concatenate with the blues. So 0, 0, 0. So we can get 0, 0, 0. 0, 0, 0, 1. So 0, 0, 0, 1. We can take 0, 0, 1, 0. 0, 0, 1, 0. And so on. Okay, so pop quiz. Okay, is the string 1, 0, 1 in 0, 0, 1 star? Pause the video and see if you can figure it out. 1, 2, 3, 4, 5. Okay, so if you're coming back just for the ride or you solved it, you should have answered no. Okay, because whenever you concatenate strings from this set, anytime you take 2 strings, well, the strings in here all start with 0, except for the empty string. Any number of concatenations of such strings must start with a 0. Okay, so the answer is no. This is not in here. No. Okay, what about 0, 0, 1, 1? Is that in here? Try to figure it out. Again, you should say no, because there's no way to produce 2 consecutive ones. When you concatenate strings from in here, you start with a 0, okay, and you can get a 1, but then when you put the next string, it has to start with a 0. So you can't get 2 consecutive ones. So let's try another example. What about 0, 0, 0, 1, 0, 0? Is that in the set? This one is. So this is in 0, 0, 1 star. Now, why is that? Okay, well, you can concatenate any number of strings you want from in here. So let me show you. I'm going to concatenate 0, with 0, with 0, 1, with 0, with 0. So this is in here, this is in here, this is in here, this is in here, this is in here. So this string is a concatenation of 5 strings from my set, so it's in the clean star. Yes. So this is no, this is also no. Okay. So that's just to give you some experience with the clean star. Okay. So now you can take these operations, union, intersection, complement, clean star, and concatenation, and combine these sets, these fundamental building blocks, these finite sets, you can combine them in any way you want with these operations. And that's what we have done here. Okay, so let's now go and look at this expression. Okay, let's analyze that expression. So the computing task represented by this computing problem, i.e. set of strings, is if I give you a string, does the string belong in the set? Is it in the yes set? Are you going to say yes? So here's an example for you to work on. So the string, is 1 1 1 1 0 0 1 0 in this regular expression. 1 1 1 0 0 1 0 0 union 1. Okay, is it in that regular expression? And you might work hard and try to figure out how to break it down into three strings, one in each language, and so on and so forth. So go for it. Okay, and the question then becomes, okay, so I give you a regular expression that describes a language. Is there a nice procedure that we can use in order to test, in order to solve the computing problem, in order to test whether a string such as this one is in this language? Okay. Now, regular expressions are very powerful. They can express, all kinds of patterns. Okay. And you'll get practice with this in the exercises and the homeworks. Okay. But fundamentally, we then need to be able to answer the question, does a string belong to your yes set? Does a string belong to your language? Okay. I.e., that's what it means to solve the problem. Okay. So is there an easy procedure? Is there an efficient procedure to test if a string is in your language, i.e. regular expression? Okay. So that's certainly one thing that we need to be able to address. Okay. And then the other thing that we like to do is we like to define problems. Okay, because we want to work on problems, we want to define computing problems. So if I give you a set of strings, if I give you a language, can you describe it? So if I give you a problem, a language, can you figure out, for example, a regular expression to describe it? So these are two distinct tasks. Can you figure out a regular expression to describe it? Okay. So in other words, what kinds of problems can be described by regular expressions? So let's take an example. We already talked about the palindromes. So L palindrome equals the set of palindromes, binary palindromes. Try to construct a regular expression to describe this set. A regular expression to describe palindromes. That's a little bit of a trick question, and you'll see why later. Okay. Actually, I'll tell you why now. It turns out it's very, very hard to do. So, and that's why I'm using this as an example, because now I'm going to show you another way to describe sets that we have also seen before. Regular expressions are new, but another way to describe sets is using recursive definitions. Okay? So let me use a recursive definition to describe this set. And it turns out that recursive definitions are going to be related to something we will discuss later called context-free grammars, context-free languages. And those are very important in compilers and so on and so forth. So let's recursively define palindromes. And again, this is review. So recursive definition of palindromes. Okay. So, as usual, there's a base case. So the empty string is a palindrome. So this is, we call this the base case. Okay. And now we have the constructor rule. Okay, so, how do I get new palindromes from known palindromes? So if X is a palindrome, okay, then it turns out that there are two constructors. There are two things that I can conclude are palindromes. 0, X, 0, and, epsilon, 0 and 1 are palindromes. Okay, so empty, the string 0 and the string 1, they're all palindromes. So those are my starting guys, my primordial ancestors. Okay. Now if X is a palindrome, then 0x0 is a palindrome, and 1x1 is a palindrome. Okay, and nothing else is a palindrome. So this is the constructor. Okay, and remember the default clause, minimality. Nothing else is a palindrome. Okay, so let's see this set of palindromes. Well, it starts, so L-pal starts with my base cases, my primordials, epsilon 0, 1. Okay, and then, I can take any of these and add 0 to both sides. So if I take epsilon and add 0 to both sides, I can also add 1 to both sides. So I get 0, 0, 1, 1. I get 0, 0, 0, 0, 0, 0, adding 0 to both sides. Okay, I can add 1 to both sides. I get 1, 0, 1. I can add 0 to both sides. 0, 1, 0. I can add 1 to both sides. 1, 1, 1. And so on. Okay, and if you want to get practice with your recursive proofs and so on and so forth, you can use structural induction to prove that everything in this set is a palindrome. And then you can also use another kind of induction, well-ordering principle and contradiction to prove that every palindrome is in this set. So, or take it from me that this is a valid recursive definition of the set of palindromes. Okay. So let me give you some. So this is sort of, we've switched gears. We talked about describing, we talked about ways of describing languages called regular expressions. And, if you're given a string, the computing task is to decide whether or not it's in your language, whether or not it satisfies the regular expression. Now we kind of switched gears. We said, okay, well, how do we define certain languages that are of interest? Okay, and I asked you to try your hand at defining palindromes, find a regular expression for palindromes. Okay, I gave you another method for defining languages, which is recursive, and we found a very nice, compact, easy definition of palindromes using, the recursive definition. So let me give you some problems along this vein. Okay, so I'm going to show you two sets. I'm going to use string patterns to describe these two sets. So I'm going to call this L1 is, the set 0 to the n, 1 to the m, where n is greater or equal to 0, m is greater or equal to 0. Okay, so some number of zeros followed by some number of ones. And it could be 0, 0, and it could be 0, 1. So epsilon is also in this set. Okay, L2 is equal to 0 to the n, 1 to the n. Okay, so this is, where n is greater or equal to 0. Okay. Okay, so what is this? So this is just some number of zeros followed by some number of ones. So, exercise. Okay. Give regular expressions that describe these languages. 1. Give regular expressions. And 2. Give recursive definitions, recursive sets. Give recursive definitions for these languages. Okay. Okay. And turns out that these languages look very similar. So they're very similar looking. So these languages look very similar. Look, it's a bunch of zeros followed by a bunch of ones. Okay, a bunch of zeros followed by, in this case, an equal number of ones. They look very similar. Strings of zeros followed by ones. It turns out that these two languages are very different. Okay? Very different. So even though they look very similar, they are very different languages. And I could ask you, well, it turns out that one of them is much more complex than the other. And, you can pause the video and try to guess which one of these is more complex. Okay. And, I'll give you so I'll pause the video, 1, 2, 3, 4, 5. If you're coming back just for the ride, you might have thought, oh, this is more complex because it involves two variables, n and m. No. Turns out that this is way more complex, even though it involves just one variable. Okay. And that's because, here, n and m are arbitrary. Okay, so it's just a bunch of zeros followed by a bunch of ones. Here, somehow this language embeds the notion of equality. So n must equal m. So m must equal n. That's why it's 0 to the n, 1 to the n. So this language is more complex, but we have no idea what that even means. Okay, what does it mean that the language is more complex? Okay, so when you try to give regular expressions for both of these, you'll find that for the more complex language, it's going to be very hard to come up with a regular expression. Just like it's very hard to come up with a regular expression for the palindromes. And when I say very hard, I mean very hard. I mean impossible. Okay? And you might say, what? There's no regular expression for this? Yes. For this equality, there's no regular expression. Is there no regular expression for palindromes? Yes. There's no regular expression. And we'll prove it later. Okay? But recursive definitions, no problem. You can come up with recursive definitions for both of these. Okay? And that suggests that, in some sense, if you view regular expressions as a nice, convenient, simple way to describe languages, then this is simple, this is complex. Okay? If you view recursive definitions as a complex way to define languages, complex, very powerful, then it's powerful enough to describe both. Okay? But, there are two messages here. So we won't get into those details yet, but there are two messages here. Okay? Well, the first is, what is the complexity of a language? What is the complexity of a language? Okay. So we're going to have to sort of try to define that. And why do we care? Why do we care? Okay. And so the why do we care is actually much easier to answer. Okay. Why do we care is, well, remember where languages came from. Languages came from computing problems. Okay. And, computing problem was this vague sort of notion of you feed in an input and you get some output. Well, now we pinned it down. A computing problem is a decision problem. Okay. So a computing problem is a decision problem. Okay. Well, but then what is a decision problem? A decision problem is just a language. This is just a language, the yes set, the language. i.e. the yes set. Okay, so that's what a decision problem is. Okay. And we're on our way towards trying to understand which kinds of computing problems are hard, i.e. impossible, and which kind of computing problems are easy, i.e. possible. Okay. And along the way, we're going to see a whole spectrum of problems going from easy to sort of slightly harder, and then to impossible. Okay. And we want to sort of be able to quantify how hard is a computing problem, and it boils down to basically saying how hard or complex is the language, is the yes set that is associated with that decision problem. So if we have a way of, describing or defining or quantifying the complexity of a language, then we have a way of quantifying how hard a computing problem is. Okay? And so let me give you a sort of taste for what we're going to do next time. So in order to for the rest of this class, in order to define the complexity of a language, that brings us to models of computing. Okay? So let's now talk about the complexity of a language. So the complexity of a language, i.e., how hard is the corresponding computing problem. Okay. So we're trying to define how hard is a computing problem, which is related to the complexity of a language, and what would it mean for a language to be complex? So remember what's our goal? Our goal is to take a set of strings, a language, a problem, becomes a language. Okay, and what's the goal? You're going to feed me an input W, and I have to say yes or no. So we can say the problem is hard or the language is complex if the task of saying yes or no to whether an input W is in the language, if that's a hard task. If it's an easy task, the problem is easy, the language is simple. If it's a hard task, the problem is hard, the language is complex. Okay? And what does it mean, a hard task or an easy task? Well, it's an easy task if we can build, let's say, a simple machine to solve it. It's a hard task if we cannot build a simple machine to solve it. Okay? So let's work with an example. So remember that push guy, that push light. So the language for the push light. And remember now, the language defines the problem. You can forget about the fact that it came from the push light, but the language defines the problem. The push light problem is the language 1, 0, 1, 1, 1, okay, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, and so on. Okay. And there's a very easy way to describe this set of binary strings, okay, which is all binary strings that end in 1. Binary strings ending in 1. Okay. So, is this a complex language? Is this a simple language? Is this a hard computing problem? Is it an easy computing problem? So let's see. Let's try to sort of build some, simple machine and see if it can solve this problem. So I'm going to build a simple machine. Okay. And I'm going to show you this simple machine in sort of a graphical way because we're used to graphs. It's another beautiful application of directed graphs. Okay. So, I'm going to imagine a vertex. Let me call this vertex Q0. And I'm going to imagine another vertex Q1. Okay. And, I'm going to imagine that my machine is represented by these two states, Q0 and Q1. So think of my machine as having two states. Okay. In some sense, I'm building a very primitive CPU. So I have two states. Okay. Q0 and Q1. Okay, and just like in any computer, but this is not a computer, this is just a machine. In any computer, you have, machine instructions. Okay, I'm going to represent my machine instructions, with arrows. Okay, directed graph. Okay, so, I'm going to show an arrow which, is linking Q0 to itself. So there's a self loop here. Okay, so it's a more complex graph than we have seen so far. So what does this instruction say? It says that, if you're in state Q0 and you happen to see a 0, stay in Q0. So if in Q0 and C0, stay in Q0. Okay. If you're in Q0 and you happen to see a 1, move, change states. Okay. Change states to Q1. Okay. Now, if you're in Q1 and you happen to see a 1, stay in Q1. If you're in Q1 and you happen to see a 0, switch states back to Q0. Okay, so if in Q0 and C1, jump to Q1. So move to Q1. Okay, now if in Q1 and C0, jump to Q0. Move to Q0. If in Q1 and C1, move or stay in Q1. Okay, so you can think of those as instructions of what to do in the event that you see zeros and ones. And why are we talking about zeros and ones? Because, the inputs to this problem, the input is a string of zeros and ones. Okay. Now, the point is, this is just a state transitioning machine with 4 very simple instructions. It's kind of like a vending machine in some sense. And so you might think that this is easy to implement as a mechanical device. So this is a very simple machine. A very simple machine. Now, what I'm going to do is I'm just, bear with me. I'm just going to color this, I'm going to put a sort of a green border around this state. So the way we will represent states like this. So some of the states have a green border. So let me just put a green border here. Okay. And I'll, from now on, not draw the green border, but just once, let me show you this nice colorful green border because I'm so good at coloring. Okay, look at that beautiful coloring, Bob Ross style. Okay, so here's a very simple machine with 2 states, the regular Q0 state and the green Q1 state. Okay, and some 4 instructions. Okay, so now what's the use of this machine? So, well, let me also tell you that I'm going to start my machine in my state Q0. Now, what's the use of this machine? Okay, so let's consider some input strings to my problem L push. Remember what the task was. The task in L push was, if I give you a string, tell me whether or not the light is on. So if I give you a string, is the string in my set? Okay, so let's consider a few strings. Let's consider the string 0, 0, 1, 1, 0, 1, and 0, 0, 1, 1, 0, 0. Okay, so you can imagine that, associated with this machine is what we call a read head. Okay, so that's also not so hard to build. Something that can just look for inputs. Okay, so you can think that the read head starts here, the read head starts here. Okay, so now let's see what happens on this string. If it's so every time it sees a bit, it kind of gobbles it up and moves to the next bit. So it sees a 0. Okay, so it started in state Q0. It sees a 0, and it says if you're in state Q0, okay, stay in Q0. So it stays in Q0. Okay, so I'll put my finger on where the current state is. So I see a 0, I stay. Okay, I see a 0, I stay. I see a 1, I jump. I see a 1, I stay. I see a 0, I jump. I see a 1, I jump. Nothing more, I'm done. Okay, so at the end of this string, we will say that your state is green, i.e. Q1. Okay, let's see what happens at the end of this string. Okay, I see a 0, I stay. I see a 0, I stay. I see a 1, I jump. I see a 1, I stay. I see a 0, I jump. I see a 0, I stay. At the end of this string, I am in state Q0. Now I'll give you some exercises. Okay, figure out what happens with the following strings: 1, 1, 0, 0, 0, 0, 0, 0, 1, or 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0. Okay. Pause the video. Figure out what happens with all of these states. Classify each of these states into green Q1 or black Q0. Okay, 1, 2, 3, 4, 5. Okay, so you've done it. So I'll tell you, I won't even go through the machine because I constructed the machine. I know this machine. I am at one with this machine. Okay, so here you should have got black Q0. Here you should have got black Q0. Here you should have gotten green Q1. Here green Q1. Here green Q1. Here you should have gotten black Q0. And now, what you will observe is a very interesting phenomenon. Okay, these strings, which gave me black Q0, none of those strings, 1, 2, 3, 4, none of those strings are in L push. Okay, and the strings that all gave me green Q1, okay, and green Q1, all these strings are in L push. So when you run the string through this machine, by looking at where this machine ended up, are you in green Q1 or are you in Q0? Green for yes. Okay. If the machine ends up in the yes state Q1, you answer yes, and you'll be right. The string will be in L push. If you didn't end up in Q1, if you ended up in Q0, you answer no. And indeed, it's the case that, all the strings for which you answer no will not be in L push. So, what we say is that this simple machine simple machine solves the problem L push. Okay. Now, that suggests that L push is a very simple language. Now, for all the languages that we saw, 0 to the n, 1 to the m, palindromes, 0 to the n, 1 to the n. So some of the languages that we saw, you can go and see if you can construct a simple machine like this in order to solve the language, in order to solve that computing problem. Okay. We'll discuss this next time. Okay. But let's summarize. Okay. And this is the important summary of today. Okay. So we defined a computing problem as a decision problem. What is a decision problem? A problem to which the answer is yes or no. That means that we can, divorce ourselves from the actual problem and just focus on the yes set, the language that comprises all strings for which the answer is yes. We call that the yes set, and we defined abstractly a language is a computing problem. So you give me a language, you've given me a computing problem. We saw ways to describe languages, i.e. ways to describe computing problems. Okay. So we've seen in this class lots of computing problems, and we have a very precise definition of a computing problem. And then what's a complex computing problem? A complex computing problem is one that's associated with a complex language. And what's a complex language? Or what's a simple language? A simple language is a language for which you can easily test membership in the language. And why do we care about testing membership in the language? Because that's what it means to solve the problem. If I give you an input to my problem, which is a string, you should tell me yes or no. And if the language is simple, it's easy to tell me yes or no. Okay. And what we see here is that we can now start talking about the complexity of a language by how simple it is that how easy it is to construct a simple machine to solve that language. Okay. And then we might ask, well, what happens when the language gets more complex? Okay. So if a language gets more complex, maybe you can still solve it with a machine like this. You can think of this as a state transitioning machine, simple mechanical device that bumbles around from state to state. And somehow the ending state encodes yes or no. So there's a green state. Okay, well, you might not be able to do it with a machine that just has 2 states. Maybe you need 3 states. Maybe you need 4 states, 5, 6, 7, and so on. That means you need more resources to solve the problem. Okay, that kind of more complex computing problem where we talk about we need more resources, well, you'll study more about those kinds of computing problems in an algorithms course. Okay, but then there's another kind of more complex problem, okay, which is, is it possible to solve the problem with a state transitioning machine? Okay, if not, you need a totally different machine. You need a more complex machine. Okay? That's the kind of complexity that we are going to focus on. So we're going to ask the question, can all the problems we are interested in be solved by such simple machines? Or, if so, then we're done. We'll be done early with this class. Or, are there problems that we cannot solve with such simple machines and we need a drastically new kind of machine with new capabilities and new power in order to solve those problems? Okay. So this is an example of what's called a model of computing, and that's going to take us deep into the whole, context of models of computing. So we're now moving into the context of models of computing. That's what's next. But before we can even talk about models of computing, we had to define what is a computing problem. Okay, and that's what we did today. Checking out.